Now let's go to solve this kind of problem, to train ourselves with the idea, with the concept of a vector field. A vector field exists in space when at every point in space you assign a vector. So let's go to do problems. Now the first problem is asking, given the vector field I plus j, how you will describe this vector field I plus j? And it say, what is the magnitude of the vector field? Well, the vector field exists at any point in space. What is the vector field that exists at the position 1, 0, I plus j? And what is I plus j? I plus j, 1 meter to the right, let's say, and 1 meter up will configure a vector that is the vector 1i plus 1j. And what is the vector field here? Same, I plus j. And what is the vector field here? Same, I plus j. I'm here. Same, I plus j. I'm here. Same. So this is a vector field that could be something like a wind flowing, and it's flowing all over the space with the same direction. And what is the magnitude? Well, the magnitude of f is the square root of 1 square plus 1 square, which is 2, so it's the square root of 2. So this vector field is the vector field whose direction is always 45 degrees, and whose magnitude is always the square root of 2. Now let's go to the next problem. The next problem say the same, but now it's in 3 dimensions. In 3 dimensions we have a vector field. Who is the vector field I plus j plus k? Well, I is 1i. J is the vector field 1j. And k is the vector field 1k. And what is the vector? The vector is the vector that is the sum. So this is the vector field. This is the vector field 1i plus 1j. It's to visualize the vector, it's better maybe to do like this, to draw something like this, and the vector goes from the origin to this vertex, 1i, 1j, and 1k. 1i plus 1j plus 1k will be this vector, the vector that goes from this point to this point of the corner. And this same vector, it exists all over the space. So describe the vector field I plus j plus k is the vector that goes in this direction, this one, going from 0, 0 to the point 1, 1, 1. And it exists at any point in space. And what is the magnitude? Well, the magnitude of a vector is the square root of the square of the components. So it's 1i, 1 square, plus 1j, 1 square, plus 1k. The component is 1. The zeta component is 1. So it's 1 square, so it's the square root of 3. So this is the magnitude. So to describe the vector field, we can say that the vector field is a vector field whose magnitude is the square root of 3, and whose direction makes through the x-axis makes 45 degrees, and to the theta axis makes an angle that is here. You see, this is the angle, and what is the angle? This angle. Let's go to find this angle. So we can see the triangle, this triangle here, this, and the square root of 3. So this triangle have the side 1. Now it has the side square root of 2, because this side, that it will be a square root of 2, this side is 1, a square root of 1 plus a square root of 1, 1 square plus 1 square root. So this is a square root of 2. And this side is a square root of 3. And this angle, that is the angle that we need to describe the vector field, is such that the tangent of theta is a square root of 2 divided by 1. And who is the angle who tangent is the square root of 2? Well, you need to use a calculator. So theta is arctangent of a square root of 2. And arctangent of a square root of 2 is like 50-something degrees. 54, I use the calculator, 54.73 if I'm not wrong. So how we will describe the vector field? Well, we may say that this vector field 1i plus 1j plus 1k is the vector field that have the magnitude square root of 3, does 45 degrees with the x-axis. And the vector field, this one, the one that will go from this point to the corner of the cube, this angle should be 54.73. So in that way we can define the vector field. Let's go to the next problem. Well, before going to the next problem, let me say that maybe one person could say intuitive that this angle should be 45 also, but it's wrong. It's not 45, it's 54.73. Okay, next problem. We go to vector field. What is the recipe that we have to distinguish between vector fields that are conservative for those who are not conservative? You take the components, the x component of the vector field, you take the y component of the vector field, and you do the partial derivative of the x component with respect to the y. And you do the partial derivative of the y component with respect to the x. If these are equal, you are done. The vector field is conservative. If not, it's not conservative. Now it's almost a rule, but later on I will prove that if f is conservative, then f can be written like the gradient of some function that we name as the potential. And if f is the gradient of some function that is the potential, this thing will happen. Okay, let's go to apply it. Let's go to discover who is fx. Fx is the x component of the vector field. And what is the x component of the vector field? 5y cubed. Who is fy? Fy is the y component of the vector field. What is the y component? Is 5y squared multiplied by 3x. Or in other words, 15y squared x. And what is the partial derivative of fx in respect to y? Is 15y squared. And what is the partial derivative of fy in respect to the x? Is 30 y respect to the x is 15 y squared, sorry. Is 15 y squared. So are they equal? Yes. Is the vector field conservative? Yes. So we are done. Later on we will make the proof. Now we are going to do problem number 4 that is more or less the same. Who is the x component of the vector field? The x component of the vector field is 1 or x squared plus y squared minus 1/2. Who is the y component of the vector field? The y component of the vector field is, again, x squared plus y squared minus 1/2. What is the partial derivative of the component x of the vector field respect to the y? Is minus 1/2 x squared plus y squared raised to minus 1/2 minus 1 is minus 3/2. Minus 1/2 minus 1 minus 3/2 multiplied by 2y. Okay, what is the partial derivative of the component y respect to the x? Is minus 1/2 x squared plus y squared multiplied by 2x raised to the power minus 3/2. Are they equal? No. No, they are not equal. So this vector field is not conservative. Conservative means that the line integral over a closed path will be 0. And also it will mean that you will not be able to find the potential f of xy whose gradient is the vector field. Not possible to find the function f, the potential. Now, problem number 5 say, find the conservative vector field for the potential function f of xy equal x squared minus 1/4 y squared. If they say that exists a potential function, it means that the vector field is conservative. Otherwise, it will not exist. So this problem is almost the opposite. Is given the potential, given f of xy. Who is the vector field? Well, the vector field is simply the gradient of f. The gradient of f in mathematics is the vector field. If f represents force, the force is minus the gradient of f. But in this case, the gradient of f is the vector field. So it will be the partial derivative of x, of f, of x squared minus 1/4 y squared I plus the partial derivative respect to the y of f of x, x squared, of f of xy, x squared minus 1/4 y squared. And what will be this? So the vector field f, that is the gradient of f, it will be the partial of respect to the x. Here I see a 2x, and here I see a 0. So it will be 2xi. Here I will see the partial respect to y, this is 0. And here we will see 2 times 2 4 1/2 I plus y divided by 2 j. So this is the vector field that comes from the potential that we have now. Now imagine we have a potential function that is f of x, y, and z, and we want to find the vector field from the potential. To find the vector field from the potential means to find the gradient of f. And to find the gradient of f means to find the partial derivative of x of the function c6xyzi plus the partial derivative respect to the y of the function 6xyz j plus the partial derivative respect to the c of the function f6xyz k. And what is this? The vector field will be the partial derivative respect to the x will be 6yc. 6yc in the I direction plus the partial respect to the y of 6xyc, it will be 6xc. 6xc in the j direction plus the partial respect to the c will be 6xy in the k direction. So from the potential, we have the vector field. This is the vector field. Now, if we have this problem, we'll do the same thing. Who is the potential? The potential is, in this case, is c plus y e to the x squared. What is the partial derivative of f respect to the x? Is 2xy e to the x squared. What is the partial of f respect to the y of f? Respect to the y is e to the x squared. What is the partial derivative of f respect to the z? Is 1. And what is the vector field? The vector field f is 2xy e x squared I plus the x component, the partial derivative of f respect to the y, is the j component of the vector field e to the x squared j plus 1k. And this is the vector field that we are looking from this potential. We want to discuss the following problem. It's a find a potential function for the conservative vector field. So the problem is say that this vector field is conservative. How it will look, this vector field? For example, it will look like this. At the point 1, 1, the vector field, it will be I is 1, 1i plus 1j. So it will look like this. At the point 2, 1, the vector will look like 1i plus 2j. 1i plus 2j will be this vector 1i plus 2j. So the vector will look like this. What happens if you move further? Let's say 10. If you move 10 at the point x equal 10, so the vector field will be the components of the x direction will be maintained like 1i because the y is 1. 1i plus 10 times in the j direction. 10 times. Let me change the color. Plus 10 times in the j direction. So the vector field will be like this. So as you move, the vector field, the angle is changing as you move to the right. What happens if you move up? How it will do the vector field? If you move to the point, if you maintain the x fixed and you move to the point, so as you move, the y will increase, so the I component will increase. So what will be, for example, at the point 2, 1, 2, the vector field? At the point 2, 1, the vector field x, y, the vector field will be 1i plus 2j. And what will happen at the point 2, 10? So it'll go up. So the vector field will be 10i plus 2j. So as I'm moving up, as I'm moving in the upper direction, the vector star here like 1i plus 2j, and as I'm moving up, the vector is now 10i plus 1j. It's go like this. So you can draw the vector field, but this is not the problem. The problem is to find the potential function. So the problem, in the previous problem, we have the potential and we find the vector field. Now we have the vector field and we need to find the potential. So let's go to find. So to find the potential, they say that the vector field is conservative. It means that if it's conservative, it exists. It exceeds the potential. So, okay, so let's go to find. So the vector field is equal to the gradient of the potential. Okay, so this means that fxi plus fyj is equal to the derivative of f respect to the xi plus the derivative of f respect to the yj. And if two vectors are equal, the components have to be equal. So the x component is the partial derivative of f respect to the x. In our core problem, the x component is y, and we need to find a function f whose partial derivative respect to the x will be y. In our problem, the fy should be the partial derivative of f respect to the y, but the y component is x, and the x must be equal to the partial derivative of f respect to the y. So we need to find a function f of xy whose partial derivative respect to the x is y, and whose partial derivative respect to the y is x. What would be? Well, it could be f of xy equal x multiplied by y, because the partial derivative of f respect to the x is the y. And the partial derivative of f respect to the y is the x. So, but indeed, any potential like this plus c will work. Okay, so let's go to do it completely, all the steps. If y is the partial derivative of f respect to the x, is because f of xy could be x plus y, x multiplied by y, plus a function phi that depends on y. If I add a function phi that depends on y, I can check. The partial derivative of f respect to the x will be y, plus the partial derivative respect to the x of a function that depends exclusive of y. So this will be 0. Now, for the other side, if x is equal to the partial derivative of f respect to the y, I will conclude that f of xy will be x multiplied by y plus a function phi that depends on x. So now I can check again. The partial derivative of f respect to the y will be the x, or if I do the partial derivative respect to the y of this expression, I will obtain the x, because the partial derivative of x multiplied by y respect to the y is x, and the partial derivative respect to the y of a function that depends on x, on x exclusive respect to the y is 0. So, conclusion, the potential is x multiplied by y. Then we can write f, given the vector field f, the potential f of xy is x multiplied by y plus some constant c. And c is a real constant. It doesn't depend on x or on the y. It should be c. Okay. Now we do this problem. Find a potential function for the conservative vector field. So the field is conservative. How we can check that the field is conservative? Well, the derivative of the component y of the vector field respect to the x should be equal to the derivative of the component x respect to the y. Or in other words, the derivative respect to the x of y divided by x squared plus y squared should be equal to the derivative respect to the y of the component x of the vector field, which is x divided by x squared plus y squared. This is equal. Let's go to check. So the derivative respect to the x of y multiplied by x squared plus y squared minus 1, this is equal to y minus x squared plus y squared minus 2, and the internal derivative respect to the x will produce 2x. So for this side we have this equal. Let's go to see if this is equal to the partial derivative respect to the y of x. So this is indeed equal to the partial derivative of x multiplied by x squared plus y squared minus 1. Let's go to do it to see if it's equal. The partial derivative respect to the y is x minus x squared plus y squared minus 2. Now the partial derivative of this respect to the y is 2y. So is this equal to this? Yes. Yes, I see the minus 2xy, 2yx, and yeah, so is a conservative field. Okay, so now let's go to erase here, and we find the potential. Now let me erase this, and we find the potential. So to find the potential, we have to find a function whose gradient is the vector field. So we have to find f of x comma y such that the gradient of f will be the vector field f. But the gradient of f is the partial derivative of f respect to the x by I plus the partial derivative of f respect to the yj, and this should be to the vector field fxy plus fyj. In our case, what we have is that components so if this expression is equal, is because the y component is equal to the y components. So the partial derivative with respect to the x is equal to the x component of the vector field. So it's x divided by x squared plus y squared. And now we have to write the second condition. The second condition to obtain the potential is to write this equation. The partial derivative with respect to the y, that is the y component of the gradient, should be the y component of the vector field. So should be equal to y divided by x squared plus y squared. Perfect. And now the question is, if I admit the first equation, who is f of xy? Who is the function whose derivative respect to the x is x divided by x squared plus y squared? And the question is, who is f of xy whose partial derivative respect to the x gives this expression? You see here I have the derivative of the denominator. So a natural log will work. So natural log of x squared plus y squared, if I make the partial derivative respect to the x, will be 1 divided by the function, 1 divided by this, multiplied by the derivative of the function will produce a 2x. So the correct answer is this one. 1/2 of the natural log of x squared plus y squared will give this function. But also, if I add here a function that depends on y, will also give me this expression, because the partial derivative with respect to the x of this expression will be this one again, because the partial derivative with respect to the x of this expression that depends only on y is 0. Perfect. And here, what will happen? Here, f of xy, who it will be? Well, it's have the same expression. I need to find the function whose partial derivative with respect to the y give this expression. And who is this? Is again the same one. X squared plus y squared plus, now is g of x, because if I make the partial derivative with respect to the y of this expression, I will obtain this one. So who is f of xy? Is this one or is this one? When it appears a g of x here and it appears a g of y, to accomplish both conditions, you need to put a constant c that doesn't depend on x and y, and now you will agree, you will fit both conditions. So the f of xy should be 1/2 natural log x squared plus y squared plus c. And this is the answer. Okay, let's go to the next problem. The next problem say, find a potential function for the conservative field 3x squared y squared I plus 2x cubed yj. So we do the same thing, but now we do it very, very fast. The partial derivative with respect to the x should be the x component of the force, 3x squared y squared. And the partial with respect to the y should be 2x cubed by y. Who is f of xy? Who is the function whose derivative respect to the x is 3x cubed y? Well, try x cubed y squared. X cubed y squared, the partial derivative respect to the x will produce 3x squared xy. But is this the only one? No. Maybe if I add some function that depends on y, will also work. Now, if I'm here, who is f of x and y? Who is the function whose partial derivative respect to the y will give 2x cubed y? Well, try this one, 2x cubed y squared. If I do now the partial derivative respect to the x, I will have 4x cubed y. Oh, but I have 4, not a 2, so erase the 2. Now, if I do the partial derivative of f respect to the y, will be, sorry, erase the 2, so it will be 2 times x cubed y. That is plus what? Plus another function g that depends on x. When this happens, you need to fit the both conditions. So both conditions are fit by saying that the f of xy is x cubed y squared plus a constant c. And this is the potential. Let's go to apply what we have done to gravitational fields, to gravitational force. When you have an object of mass m, and you have a small object of mass little m, there is a force acting on the body of mass m. And the force acting on the body of mass m, it has a constant of integration g. It is the product of the two mass m by m. The force is intense relative to the distance. If the distance is very big, the distance of separation between the two masses is very big, the force is very weak. So it varies with the distance square. And now the gravitational field is a force that, if you see it from m, the force, whatever is the m, the force will go in the direction connecting the two masses. Let's go to imagine that the mass, little m, is a point also, okay? But is almost a point, but there is more mass. So from the center of the big mass m. So the force is on the line connecting the two bodies. And now there is another detail. The force acting on m is an attractive force. It goes in this direction. So how we will express the direction, the vector direction that point to the mass little m is the unitary vector. But the force is in the opposite direction as the unitary vector. So the gravitational force acting on the mass little m is minus gmm in the direction of r. So how we will find the potential? To find the potential, we need to express this equation in terms of x and y. So the force on m, acting on m, not magnetic, acting on m, is minus g mm divided, so this is the origin, and this is the point which is at x and y. So r squared is x squared plus y squared. Raised to the 1, okay. R squared is x squared. And who is the vector r? The vector r is the unitary vector r. Is r divided by his magnitude. The vector r is xi plus yj. And the vector magnitude of r is a square root of x squared plus y squared. Now I can put here the vector r. put it here. Now if I put it here, I have to put xi plus yj divided by x squared, square root of x squared plus y squared. So if I put here x squared plus y squared 1/2 is the same that if I add it here and put here 3/2. Conclusion. The force acting on M of little m is minus gmm x squared plus y squared 3/2 xi plus yj. And the component x of the force is gmm multiplied by x divided by x squared plus y squared 3/2. And the component y of the force is gmm y divided by x squared plus y squared 3/2. And our problem is giving f of x and giving f of y, who is the potential energy. So in physics, to give sense to what is force, what is the vector field will point in the opposite direction as the gradient. So this is minus the derivative of f respect to the x. This is minus the derivative of f respect to the y. And now we wonder, who is the function f whose derivative with respect to the x will give the component x of the field? And the answer is that f of xy will be, you see, if the derivative of f respect to the x is this, it means that the derivative of f respect to the x is minus gmm x divided by x squared plus y squared 3/2. So the question is, who is f of xy? Who is f of xy whose derivative is minus gmm? Is minus gmm divided by x squared y squared 1/2. Oh, why? Well, because if I make the derivative of f respect to the x, I will obtain this. So this is the potential energy. So E sub p of x comma y is minus gmm x squared plus y squared 1/2. Or minus gmm divided by r, by the distance that separates the two bodies, because x squared plus y squared 1/2 is the distance. So the question that we can write is that E sub p of r for the gravitational field is minus gmm divided by r. Perfect. But there is something that I can say. Here, I may say that if I add a function phi that depends on y will also work, because the derivative will be. So, at the end, the function will be, even if I consider the component y of the field, meaning y divide this component y, and I do the same thing, I will obtain the same potential energy. So the potential energy is E sub p, the F that is the potential energy will be gmm minus divided by x squared plus y squared 1/2. And the problem is, well, the the lesson about gravitational fields is already done.